Howdy everyone. Now we're going to talk about how do we write Lewis structures so that we can get an idea of, well, how is this molecule put together? What does it look like? And so it's a 5-step process for the main drawing, and then there's some kind of revision steps we'll talk about at the end with formal charges. But for the first step, so that we'll always take whatever the formula is, you put the first atom in the center and connect all the other atoms to it with a single bond. So this molecule is PCl3, phosphorus trichloride. So phosphorus in the middle, each chloride on the outside connected with a single bond. The only exception of the first atom goes in the middle is if it's hydrogen for like an acid, because hydrogen will never go in the middle. Hydrogen only ever makes one bond. But for everything else, whatever goes first, put it in the middle, unless the problem explicitly tells you, oh, it goes in some other order. All right. Step number 2. We know that the outer atoms need to have an octet. So we'll go ahead and say, well, there's already 2 electrons in this bond, so let's just, well, give them 6 more. 1, 2, 3, 4, 5, 6. So we make non-bonding pairs where we put them in groups of 2 around there, and we do that for each of the outer atoms. 6 dots as we go. Now each of those chlorine atoms has 8 valence electrons around them. All right. Step 3 is where we got to do a tiny little bit of math. This is where we're going to add up all the atoms we're supposed to have, including charge. If a plus or negative charge for a polyatomic ion says, ooh, add some electrons in or take some away, we're going to adjust for that. So we see here, okay, phosphorus, how do we get that? We look at the A labels on the periodic table. Phosphorus is under column 5A, so it brings 5. Chlorine is under 7A, so each of them brings 7, so that's the 3 times 7. We add that all up, there's supposed to be 26 electrons drawn total, 26 valence electrons. We check to see, well, do we have them all drawn? Are we missing any? And so the book here says, oh, they say, well, 6 of them are in these 3 bonds, so that's where they subtract off 6. We have 18 more that were non-bonding. Well, that gets us 2. I prefer to count by 8, where we say, hey, the chlorine, we gave it an octet, so that's 8, and then 16, and then 24, and we would just do 26 minus 24 equals 2. But regardless of which way you do it, we are missing 2. Again, if there was a charge, we'd adjust up or down for this number. How many are we supposed to draw? All right, so we're missing 2. Where are they? What do we do with them? Well, that's step 4. If there's any missing electrons, where that we have to add in, put them on the central atom in pairs. So we need it 2, so the 2 go together right there on top. And now for step 5, and this is the key word here, if. If the central atom does not have an octet, then we'll try moving electron pairs from the outer ones and to make a double bond or a triple bond or whatever. But because we look at this phosphorus and say, oh, 2, 4, 6, 8, there are 8 electrons around it, it has an octet, we don't need to do anything with double bonds. So step number 5 is the tricky one where most people mess up. They'll say, oh, a double bond looks good, and they'll just do it before they put dots in, before they count, does it have an octet? So always do the counting first. That will let you know if you need to even do step 5. In this case, you can always double check at the end. We have 8, 16, 24, 25, and 26 electrons. We were supposed to have 26. We're good to go. I know. What about if we did need to? So here's an example. This is hydrogen cyanide. It's a poisonous gas. Don't breathe it in. And so if we follow steps 1 through 4, this is the picture we would get, where it would be a bond to the hydrogen, a single bond to the nitrogen. The nitrogen would have 6 valence electrons around it, and that is 10 electrons total. And that's what we're allowed to draw. So we can't just add in dots on this carbon, even though it's only got 4 valence electrons around it right now. And since we can't just add them in, we can only move them. So you can see here, based on these arrows, these 2 are moving to make a double bond. Well, that would be 2, 4, 6. And so then they also move these 2 to make a triple bond. And so you can see in this picture over here, 2, 4, 6, 8. Now there's 8 valence electrons around the carbon. There's still 8 around the nitrogen, right? It was 2, 4, 6, 8 here. It's 2, 4, 6, 8 over here. So when we move these, the rules are they have to still stay connected to the atom they started with. So these 2 were with the nitrogen. when they go to make a bond, it still has to be a bond from nitrogen so that nitrogen doesn't lose any. But that's how we can use a triple bond or a double bond to get this done. So just one more example I'll do, maybe from scratch so it's a little bit easier. Now I'm going to do sulfur dioxide, SO2. So we put sulfur in the middle. We put one oxygen on either side. We go ahead, step 2, give each oxygen an octet by adding in the 6 more electrons in 3 pairs. So that's 2, 4, 6, 8, 2, 4, 6, 8. We do our counting. Sulfur is under 6A, so that's supposed to bring 6. Oxygen is also under 6A, and there's 2 of them, so 2 times 6. We add that all up. We are supposed to have 18 electrons. If we count 2, 4, 6, 8, 10, 12, 14, 16, so when we subtract that, okay, we're missing 2. Well, any electrons that need to be added go on the central atom in pairs, so there's the 2 dots there. And now step 5, we check, does the sulfur have an octet? 2, 4, 6, no it doesn't yet. So we'll say, okay, I'll pick, say these 2 here on the right, I'll move them down and make a double bond. So I'm going to go ahead and erase those and then move them. Right? So erase, move them, and they'll go to form now a double bond. And now it's still, do we have 18 total? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, we do. Does everything still have an octet? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything's got the octet. That structure is good. All right, so that's how we draw the basic structures. Now, sometimes we have an issue of, well, why did I draw it from this one here on the right? Could I have drawn it from the left? Could I have done a triple bond? Could I have done something else? And so we do have some additional rules of how do we get the best picture. And that's where we get formal charges. And so a formal charge is what happens if the bonds are all shared equally. If we say there's 2 electrons in that bond, but then we split them. So one atom or one electron goes one way and one electron goes the other as far as counting. So they give us the equation that the formal charge is how many valence electrons an atom is supposed to have. So I'm going to go ahead and add in here, this is the A label number, right? So 4A, 5A, 6A, it's that A label. Then you subtract half the bonding electrons because we're splitting those bonds in half, 1 each. And then all of the non-bonding, they all get subtracted off. And so if we look here, carbon dioxide, this is a possible structure. And oxygen, it's supposed to have 6. It's under 6A. If we count how many are assigned to it, we say 1, 2, 3, 4 because of the 4 non-bonding. And then we have 2 from these bonds. We split the bond in half and say, oh, there's 1, 2. And so that's 6 electrons that are given to oxygen. Well, 6 minus 6 is 0. Same thing with the carbon. Carbon is supposed to have 4 electrons. It's under 4A. But then we split the bonds. 1, 2, 3, 4. Okay, 4 minus 4 is 0. And then the same thing for this oxygen, 6 minus 6 is 0. So we get all zeros there. And that's a good thing. All zeros are good. We could have drawn a structure that had a single bond and a triple bond. And if we do that, well, then we say this oxygen is supposed to be 6 from 6A. Now it's 1, 2, 3, 4, 5, 6, and there's a 7th electron. Well, that one would then have a formal charge of -1. There's 1 extra electron around oxygen than there's normally supposed to be. And then if we look at this triple bonded oxygen, it would be 1, 2, 3, 4, 5. Well, that oxygen would have a +1. And that's not normally what we want. Oxygen isn't normally positive. Now, if you look, when you add all formal charges together, they should equal the overall charge of the molecule. So carbon dioxide is 0 charge, it's neutral. So 0 plus 0 plus 0, neutral. -1 plus 0 plus +1, yeah, it all equals 0. So they're still neutral. They all have to add up to the overall charge. But we're saying, hey, wait a minute, something's weird here. Oxygen can be negative, but oxygen is never positive. What's going on? How do we know which of these pictures is best? So the rule is that the dominant Lewis structure, the most important, best Lewis structure, is the one where you have the vast majority, if not all atoms, to have a formal charge of 0. So if we go back here, 0, 0, 0, this one looks better. Now, it may not be possible to have everything equal to 0, especially if it's an ion, because ions add up to -1 or -2 or +1, whatever the charge is. So if there has to be a negative somewhere, based on how you drew it, the negative formal charge goes on the most electronegative atom. So you want to maximize your zeros and then put the negative where it should be. So if we look here at these three pictures, this one only has 1 0. It's got a -2. That's really far from 0. This one, probably not our most favorable picture. Now we have these two. Both of them have 2 zeros and a -1. So, okay, they're equal as far as that goes. But we got to say, well, on this one, nitrogen is supposed to have 5 electrons around it, but this one has 1, 2, 3, 4, 5, 6. So 5 minus 6, the nitrogen has a formal charge of -1. Over here with the sulfur, 1, 2, 3, 4, 5, 6, 7. Sulfur is under 6A, so 6 minus 7, -1. So which one is better to be -1? Well, we look back at our table of the electronegative atoms, and we find out nitrogen is more electronegative. Nitrogen wants extra electrons more than sulfur, so then this one is the better structure because it gives the more electronegative nitrogen the negative charge. So that works out. That's not to say that this doesn't contribute. The other structures do contribute. But as far as, well, what's the best one, which is the most important one, it's this guy right here in the middle. All right. So let's go ahead and say, well, what's a limit of that? So it says, this is our Lewis structure of ozone, and then the slide helpfully gave us nothing. So I'm going to draw ozone real quick. And it is bent, so I'll just kind of draw it that way. But this is what ozone would be when we draw our rules here. All right, and we'd say, oh, this oxygen has a formal charge of -1. Where we go? There we are. I'll put this in blue. -1. This oxygen, 1, 2, 3, 4, 5 around it, 6 minus 5. This one's +1. And then this one, 1, 2, 3, 4, 5, 6. This one is 0. And that's the best we can do. We cannot follow our octet rule and all that and get them all zeros. This is what it's got to be. And what this says is, hey, wait a minute. This is a double bond. These two oxygens should be closer together, more strongly pulled together because of the extra bond. This bond should be longer. But we don't see that. What we see when we measure this with X-ray crystallography or other measuring techniques for molecules, those two bonds are exactly the same. They're not different. So how do we rationalize that? Well, there's a couple ways. There's the right way, which we don't cover in this course, at least not very much. And then there's the easier but made up way. We're going to go with the made up way. So for these next few slides, it's made up. This isn't real. It's not what really happens. But it's a model that allows us to rationalize it and kind of picture it in our heads in a much more easy way that gets us pretty close to the right answer as far as outcomes, but for the wrong reasons. So as long as we understand this is a model, it's not what really happens, but it'll get me close to the right answer, okay, good enough. So this made up thing is called resonance, where we say, hey, it's a combination, just like blue and yellow combine to make green. We could say, hey, in that last ozone, I put the double bond on the right-hand side. But I could also put the double bond on the left-hand side. I could have picked the other oxygen. There was nothing there. Well, these two together, going back and forth, are called resonance structures. Different ways to describe the same molecule. And we say that the real molecule is a combination. It's an average of those different resonance structures. So if we average double single and single double, it'll be more like 1.5, 1.5. And that means, oh, they're equal, and that's what we saw in the data. The bond lengths, the bond strengths, they were equal. All right? So resonance structures, they mostly come in when you have double bonds, sometimes with a single and triple bond if you have like multiple ones. But it's mainly of, hey, I have more than one place that I could put a double bond and it's equivalent. So, okay, let me combine those. All right, so if we look at benzene, this is a very important organic one. It has 3 double bonds. You can see a top kind of bottom left, bottom right, but we could put them between the others, top left, top right, and bottom. Well, the real molecule, it's as if it's an average of those two. So we could draw both of these, or sometimes, even for resonance for benzene, we just draw a circle inside to say, hey, those three double bonds are spread out equally. And what we say for that is these electrons, when they're spread out, when it's an average of multiple resonance structures, they are delocalized. They are spread out over multiple atoms being shared equally. So again, for benzene, we don't have 3 short bonds and 3 long bonds. We have 6 bonds that are all the same distance. Everything is nice averaged out. So you got to watch out for resonance. Again, that'll come up mostly when you have different spots where you could put a double bond. A lot of times you'll see it with oxygen. So if we scroll back real quickly to my SO2, this is one resonance structure. I could have put the double bond over here on the left. That would be the other resonance structure. And so the real structure is an average of the two, where it would be like 1.5 for the bond length of each. Okay. All right, so now we have a few exceptions to the octet rule, where when we're drawing these Lewis structures, sometimes weird things can happen. The 3 main ones. We could have an odd number of electrons, because if you have an odd number, something's not adding up to 8. It's probably adding up only to 7. We do have some ions and molecules that have less than an octet. Like I said, hydrogen was okay with 2, so that's something like that. There are some other atoms that are okay with less than 8. And there are some that have more than 8, that we call an expanded octet, which I always hate that term because we've expanded the 8. It's like, no, we have 10, we have 12. That's not expanding 8, that's just a different number. What I like to say is we just have some that have to have at least 8, but they could have more. So let's look at these exceptions in turn. Odd number electrons, these are rare. The molecules tend to be more reactive because of that odd number. Whenever you have an odd number of electrons and you have this one by itself, there's another term for it. We call it a free radical. Right? So a free radical is another way of saying there's an unpaired electron in our Lewis structure. All right, and so if we say, well, which of these would be better? This structure on the left, if we count, nitrogen's supposed to have 5, 1, 2, 3, 4, 5. Oxygen's supposed to have 6, 1, 2, 3, 4, 5, 6. This one has the formal charges of 0 and 0. This one would be -1 and +1. So we would predict, for NO, nitrogen monoxide, that odd electron is probably on the nitrogen because formal charges say it's more likely to be there. All right, so that sometimes happens. It doesn't come up too often on the AP test, but it can. There are a bunch that have fewer than 8. So usually we say, this is like the boron column. Usually boron and aluminum are the big ones for this. Sometimes they might bring in gallium, but it's usually just boron, maybe aluminum. And so if we draw, say, boron trifluoride, we would draw this picture. And we'd say, hey, the boron has 2, 4, 6 electrons around it. Hey, that's not the octet rule. But if we move electrons from the fluorine to make a double bond, so we would have 3 possibilities, so 3 resonance structures, this fluorine would have a formal charge of +1. And then this one would be +1, and this one would be +1, and the boron would be -1 for all of them. Well, this one has formal charges of 0. This one's better. And so we usually say for column 3A, for the boron column, it is okay to only have 6 valence electrons around that boron or around the aluminum. If the formula makes you have more than 6, okay, go with it. But if you're just drawing, don't move extra electrons there to make a double bond. You don't need to. This is the most important structure, so we go with it. All right? These do contribute a little bit, but as you can see, they're equally spread out. All right. So yeah, there's our rule. If filling the octet results in a negative formal charge on the central and positive on the outer, just don't do it. So, think about it. Fluorine's the most electronegative atom. It should never be plus. It just never should be. All right. Let's see. If we have more than that, so more than 4 bonds, so I don't know, the title still says fewer, but let's switch that over. More than 8 electrons. What we say is that it can use d orbitals if it's in row 3 through 6. So this does not work for carbon, nitrogen, or oxygen. That doesn't work there. But if we're in the 3rd row or below, silicon, sulfur, phosphorus, chlorine, bromine, arsenic, all those other ones, then they can make 4 bonds, or more than 4 bonds, because we say, hey, that 3D orbital, which is empty, it's not too much higher than the 3p orbital at this time. Maybe some of the electrons can go into the 3D. And so if we look with PF5 here, this is what we would draw, where we say, okay, just put the 5 fluorines around it, follow the same rules we did. Connect with single bonds, give them all an octet on the outside, count how many we're supposed to have and compare it to how many we do, and this is what you would get, and it's fine. We say that they're hypervalent. Valent is just how many bonds are connected to it, and since the octet is supposed to be our limit with 4 bonds, well, it's above 4. Hyper means you've gone beyond what you're supposed to, or it's a very high level. So it's a high level of bonds. Hypervalent, 5 bonds here. For phosphate, we have this structure here, where it's all single bonds, and hey, we got +1, -1s. You know, not terrible. Oh, but we could make a double bond to one of the oxygens. So we would actually have 4 possibilities for this resonance structure, and there we go. Now the book notes, I think that, there's debate, well, is this really better? Because formal charges, they're a thing we made up to try to explain things better, and it usually works. But the book notes, like, maybe this one here on the left is actually the better structure, even though the formal charges aren't as close to 0 as they could be. It depends. Again, all Lewis structures contribute. They just don't always contribute equally. All right? But yeah, if you're above 8 electrons, that's okay if you're in the 3rd row or below. All right? We're now going to talk about bond enthalpies. Officially, according to our strict definition, the bond enthalpy is the energy required to break the bond, to pull the 2 atoms apart. That means the bond enthalpies will always, always, always be positive, because that's by definition. All right? And so these are averages. Now, there's a mistake here in the PowerPoint. I don't know what this symbol was supposed to be. Well, it's supposed to be a single bond, and only the oxygen single bond worked. But these are all single bonds you see here in the table. Right, single bonds. So you can see, okay, carbon-hydrogen, very strong, 413. Carbon-carbon, 348, pretty good. But then we get some weaker ones. We get some stronger ones. So carbon makes strong bonds. This is important. This is why carbon's really good at making organic molecules. It makes strong connections. Other bonds, much weaker. So these bonds tend to be more reactive. They're easier to break apart. Right? We say that the halogens tend to be very reactive. Well, fluorine single bond, only 155. It does not take much to pull those apart. Right? Bromine at 193, chlorine at 242. So these things can be pulled apart much more easily. That's why they're more reactive. If we go, here's some more single bonds. So here's iodine, 151. So that's pretty weak. We have some decent numbers here for silicon and oxygen, all those. But then we get to double and triple bonds. So if I interpret the quotes are double. So this is a C-C double bond. Hey, now it's even stronger, 614 compared to the single bond, 413. This comma, I think, is supposed to be the triple bond. So this is C triple bond, all the way up to 800 now. That's a very, very strong bond. The most important one, N-N, triple bond. This is the dinitrogen that's in the air. Why is it so unreactive? Well, because, hey, it takes 941 kilojoules per mole to pull them apart. That's a ton of energy. And you usually don't get much energy back out of it, right? The other nitrogen bonds, well, they're very weak. Now, if you notice for oxygen, this is the O-O double bond, and that's the oxygen we breathe in the air. It's about 500. That's pretty strong. You say, but wait a minute, oxygen's pretty reactive. If this is a pretty high number, why is it so reactive? Well, look at the other bonds that oxygen makes. A carbon-oxygen double bond is 800. A triple bond's over 1,000. Over here, the silicon-oxygen single bond is 368. It's in the same ballpark. So yes, it takes a decent bit of energy to break this, but you can get so much energy out. Think about carbon dioxide. You get 2 of these. Well, that more than makes up for the amount of energy you got to put in. So that's why oxygen can be more reactive. It forms very, very strong bonds. So the thing to remember for bond enthalpies, these are by definition how much energy you put in to break them, But that means when you put them together, you get the equal but opposite amount of energy back out. So if we make a carbon-oxygen double bond, it's a negative 799. When we make a nitrogen-nitrogen triple bond, it's negative 941. This is why a lot of explosive compounds are based on nitrogen. They make this. And so this is all the energy that the explosives are releasing. It's this energy from forming that nitrogen-nitrogen triple bond. So I think we'll do, I think we're almost done actually, yeah. We'll talk about this and then we'll go back and do a practice problem with those. Where we have in general trends, multiple bonds are stronger than single bonds. So here's nitrogen, weaker, stronger, even stronger. We get average bond lengths. The stronger the bond is, or the more multiple bonds, the atoms get closer together. So here in a single bond, it's about what? About 1.47, 1.48 angstroms apart. A double bond, now it's only 1.23, 24. And then for a triple bond, 1.1 angstroms apart. So the more bonding, they get pulled closer and closer together because there's more sharing electrons going on, being held together more tightly, and it's more stable. It takes more energy to pull them back apart. All right? I just want to do a real quick example here because this is going to be in a problem set, whether it's college or AP, this will be on a problem set. Just for how much energy to break a bond and then reform it. So if we just had something like, I'm not even going to do a real reaction, but if we had like carbon monoxide plus, actually, yeah, let's do a real reaction. 2 carbon monoxides plus oxygen goes to 2 carbon dioxides, and that's 2 double bonds there, right? That's COO. This is O double bond O, right? If we draw them all out. Well, what we're saying is, okay, in order to do this reaction, I have to break the triple bond here, and I have to do it twice because there's 2 of them. I have to break the OO double bond, but then I have to make 1, 2, 3, 4 CO double bonds. And so if we do that, we can estimate, this is Hess's law again, we can estimate what will be the enthalpy change for that reaction. So if I get out my calculator and I can write here on the side, okay, to break the CO bonds, we find CO triple bond, where was it? Down here, 1072. So we have 2 times that. That energy has to go in. We also have to add in how much energy to break the OO double bond. Okay, that's 495. But then we're going to subtract making 4 carbon-oxygen double bonds because we're making the bond so that energy is being released. Sometimes what I'll also do with this is just say, hey, add up everything you're breaking, add up everything you're forming, and then do the breaking minus the forming, just so you know. Just always remember that definition. Breaking bonds is always a positive energy. Making bonds is always a negative. So we have negative for making these bonds 4 times 799. And so if we add this up, okay, 2 times 1072 is 2144 plus 495. So it's going to take us 2,639 kilojoules per mole to break this stuff. But then 799 times 4, we're going to subtract 3196 to make it, well, in that case, 2639. This reaction of turning carbon monoxide into carbon dioxide would be negative 557 kilojoules per mole. This would be expected to be exothermic. It would release energy to do this. All right, so we can predict some delta H's based not just on heats of formation, but we can go down to what bonds are we breaking, what bonds are we forming, and we get a pretty good number. The key is these are average bond enthalpies, so they're averaged from different molecules. So a given CO triple bond, it probably won't be exactly 1072, but it will be in that ballpark. Oxygen double bond, well, that probably was measured from oxygen in the air, so that number is probably more reliable. But for others, it's an average. But this will get us close to say we expect it around negative 557. And if we actually do this reaction, if we got anywhere from 530 to 600, I'd say, yep, we're pretty good there. All right, so that is the end of chapter 8. There's a lot of stuff in here, especially with the Lewis structures and the formal charges, so make sure you practice with those, and minimizing formal charges, making sure you have the octet rule, all that stuff. We'll be doing more practice in class. Until then, have a wonderful day.